So like really excited to hear the second installment. Here's Andy.
Thank you. Yeah, so let's sort of pick up from where we left off. So I'll kind of remind you the high level goal that we have is to sort of, let's say, build models that order, i.e. have spontaneous symmetry breaking at arbitrarily high temperature. Okay. And it's a sort of mathematical goal, but I think, my perspective is that if we solve this mathematical problem, then we can get kind of physical insight into how to boost, let's say, TC in a superconductor or any other phase that you might like. And indeed, today I'll sort of show you a lot of silly gimmicks, but they're gimmicks that work. They allow us to do this basically for almost any phase that we can think of. Okay. So, okay. So with this goal in mind, at the end of the last lecture, I had discussed a model of, if you will, like interacting bosons on a 2D square lattice. So at every lattice site, I have, some variable nx, which is a non-negative integer. Good. And we said, okay, let's write down the following Hamiltonian where I just sum over the number of particles on every lattice site. So this is like it costs me 1 joule, to put each particle in the lattice. And then for nearest neighbors, I have this kind of funny repulsive interaction. And we've just made this power 2 for reasons that will be clear shortly. We'll just simplify the analysis of it. And our goal is to study the Gibbs ensemble of this model. So the probability of seeing a given microstate, i.e. a collection of, we have N1 particles on site 1, N2 particles on site 2, et cetera. This is given by 1 over the partition function times e to the minus beta h, where, of course, the partition function is, as usual, just the sum over e to the minus beta h. Okay, so that's the goal. Want to understand this model. In response to maybe some questions at the end of the last lecture, the first thing that I think would make sense to do is to convince you that this model is well posed. Because we have this sort of countably infinite state space, it's not trivial. Well, maybe it is trivial, but we need to check that Z is even well defined because it's possible that it's not. So let's do that. So I want to show that this thing is finite for any non-zero value of beta. It's clearly not well defined at beta equals 0 because it's a sum over, very large, sum over integers, which doesn't exist. So we're not doing string theory. So Z of beta, a simple way we can do this, right, is to say that it's sort of upper bounded by just, let's say, the partition function when u equals 0, right? Because this term is strictly positive, so can only raise the energy. So this is a simple way to get an upper bound on the partition function. And this partition function is, of course, just the sum over all of my integers of e to the minus beta times nx like this. This is just the product over all of my lattice sites of the following geometric series, which is, on an L by L lattice, this would be the following expression, which is finite. So it makes sense to talk about the statistical mechanics of this model at any beta larger than 0. Okay, and maybe equals infinity is also fine if you want. All right. Okay. So now let's try to sort of a little bit more carefully reason out what we expect the phase diagram of this model to look like. So as a function of temperature, we want to diagnose, what typical states look like at t equals 0, as we discussed last time. We have a unique ground state. So where all the sites are empty. And now let's ask sort of what happens at very high temperature. So, okay, maybe here you just need to stare at the problem for a bit. And after staring for a while, you might come up with two guesses for what happens. So you see that, at high temperature, we would probably want to have a large number of particles, at least on average, right? Because we have this huge configuration space to explore. And yeah, so we're going to have a lot of particles in this lattice. And we know that from this U term, it's going to be very energetically costly to put them next to each other. So let's ask what the implications of this are. So we can sort of get some intuition by coming up with like two trial guesses for typical states that we might see in the in this partition function, in this sum over states. One guess would be that we form this checkerboard configuration where we just pick one of the two sublattices of the square lattice, and we put a lot of particles on each site. Okay. So let's put like n bar 1 particles on each site and ask sort of what n bar 1 would be. If we only occupy this one sublattice, right, then the U term is always exactly 0, and it doesn't contribute at all. So therefore, we can bound n bar 1 exactly, or we can just evaluate it, restricted to this class of configurations, and it's just given by the average occupation on each site, like this, which is T, the temperature. Okay, so now if we estimate what's the contribution of these configurations to the partition function, well, we can only occupy every other lattice site. So L squared over 2 lattice sites are occupied. But then we just have this partition function, for all the 50% of sites that are occupied. So we can estimate that the partition function is basically going to be order T, that's this factor at small beta, to the L squared over 2. Okay. So this is the sort of contribution to our partition function from the ordered phase, if you will. And here we're saying that this phase is ordered because we have a sort of spontaneous symmetry breaking of translations, right, where if we sort of shift our configuration over by one lattice site, it would belong to a sort of very different cluster of configurations, right, where the other sublattice is occupied. Okay. Now we can ask about another kind of configuration. So let's ask about what you might call a sort of disordered configuration, or one that doesn't break this translation symmetry, where we just put particles on every site. Okay. And if we had sort of roughly n bar 2 particles on every site, we could ask sort of what's the typical value of n bar 2 that you would see in the Gibbs ensemble. And okay, here it's a little bit tricky to do the sort of explicit calculation, but we can estimate it by saying, well, the exponent becomes of order 1 per site when U times n bar 2 to the 4th scales as temperature. So this implies that this n bar 2 scales like T over U to the 1/4. Okay. And now we can estimate again the contribution to the partition function from these kind of gas configurations where all the sites are occupied. And this contribution would scale as basically n bar 2 or T over U to the 1/4 times L squared. Now you can see why it was sort of convenient to choose this power 2 in the Hamiltonian, because it just makes it clear that no matter what value of U we pick, these configurations are sort of always very subleading at high temperature. Okay. This is a sort of heuristic argument, of course. One can do other, maybe slightly less heuristic arguments based on what you might call a Peierls argument, and argue that if you try to nucleate like little clusters, either of this phase or of the opposite sublattice phase within the solid, that the free energy cost is sort of very large. Okay. But nevertheless, I hope this argument sort of convince you that all the way out here at sufficiently high temperature, we should have what you might call a lattice solid phase, where we have this spontaneously broken Z2 symmetry. All right. What happens at sort of small but non-zero temperature? Yeah. Well, because if the scaling was different, right? If it scaled with a different, well, yeah, okay. If it scaled with a smaller power of T, then clearly, like, we would be missing a lot of configurations that could contribute, because e to the minus beta h, term by term, would be very small, or sorry, very close to 1. And if this was a sort of larger power of T, right, then already we're sort of estimating the partition function to be extremely small, because we have an e to the minus beta times T to the 1 plus epsilon. This is going to vanish very fast at high temperature. So I think this is sort of the, it's a heuristic argument, but I think this is the right standing. Well, you could do the same argument for this case. I mean, here we can do the calculation explicitly because the problem kind of factorizes on these solid, on these like perfect solid configurations. But in this case, you can also say, well, okay, if in the solid phase, this U term vanishes because I don't, at least ideally, I don't put 2 particles on adjacent sites. And then I ask sort of, when is the first term in the Hamiltonian of order T? That's sort of when the sum and the partition function gets cut off. And so you get the same. Yeah. Okay. All right. So so at high temperature, we thus have our sort of symmetry broken phase. And I think this is hopefully a sort of fairly simple model that does this. And I'll sort of unpack the physics a little bit more shortly. At low temperatures, so we have, putting in 1 particle is kind of energetically costly at low temperatures, right? We pick up a sort of penalty factor of e to the minus beta, which is very big when beta is large. So at low temperature, we should expect to see that the lattice is mostly empty, but there's a sort of very low density of excitations, of like single particles on the lattice. But if there's a low density of these particles, there's no reason for them to all kind of cluster on 1 sublattice. So we should expect that we have a disordered phase or a symmetry unbroken phase at low temperatures. So this is often called a lattice gas. Okay. And it's not a mathematically precise argument, but you might expect that there's a finite temperature at which you cross over between or transition between these 2 phases. And we numerically investigate this transition, and we find that the transition is in the 2D Ising universality class. And this is sort of a reasonable conjecture for a few reasons. Firstly, the symmetry breaking pattern is the same. So that's a sort of good argument as the standard Ising model. If you take the limit u to infinity, this model maps to a sort of well-known model in StatMech called the hardcore lattice gas. And the hardcore lattice gas is known to have a phase transition from a gas to a solid phase when the fugacity, i.e. like the preference to have a particle on one site, is roughly 3.7. Yeah.
One thing again, what the argument for gas at low temperature is.
Sure. So for the gas at low temperature, so the probability that we find even one particle on any site, we could, estimate as like e to the minus beta, and take beta to be 100, right? So this is an extremely small number. So we're going to have to go, roughly e to the minus or e to the 50 sites in any direction in the lattice to find the next occupied site. There's no reason that occupied site will be on the same sublattice as this one. So that's, yeah.
There's just many configurations that are all same energy.
Yes, yeah. So basically all the configurations with the same number of particles have the same energy. And
As long as they're not next to you,
yes.
there's no process.
Yeah.
Unlike the Victor crystal form, it is because the pattern is strictly short range that this is what.
Yes. Yeah.
Let's.
I mean, we didn't think about the case with like, some kind of long range but decaying interactions. My guess is that there's some power law, like you could get all the way up to some 1/r² or 1/r to the fourth or something before the power law would be important, but we're not sure. Yeah.
Why the
Well, because there's also an entropy gain, right? So if we just think about we're minimizing F equals E minus Ts, then the energy cost is E to the minus 50, right? But we get some entropy factor from being able to put those particles on any sublattice. So I would be very surprised if you can beat the entropy factor without a pretty slowly decaying power law. It's known that in StatMech, I don't remember all the exact exponents, but if you have power laws that decay faster than like 1/r to the d in d dimensions, or maybe 1/r to the d plus 1, it basically doesn't change the nature of a transition. So, or the nature of a phase diagram. And so, yeah, again, it's an open problem, but this is my conjecture. Yeah. Soft core.
Yeah, means I put upper limit to what nx can be. Let's say nx can be at max 1000.
Okay, so if nx maxes out at 1000, actually, I think I'm going to come back to that point. So if I don't come back to it before I stop talking about this model, then bug me again. But I think, yeah, let me return to that. Okay, any other questions on the, yeah. Yes. Yes. I would say I'm maybe cautiously optimistic, but maybe if I have time at the end, I'll say a little bit about our kind of toy model for high temperature superconductors, and that I think may sort of, it potentially relies on similar physics where you have a kind of boson whose number of fluctuations become very important. So I would optimistically hope that, the fact that we're using bosonic degrees of freedom to do this means it's not just like a mathematical trick that has no relevance, but in terms of a microscopic model that realizes this, I didn't want to do it. To be honest, I was a bit scared of like pissing someone off in the high TC community. So someone else can write this paper, but yeah.
So how do I see that? Qualitative or abstract from that?
So, I mean, from this argument, actually, we would say that the solid and gas kind of have comparable energy densities, but the entropy for here is huge. So yeah, I'll come to this point in a couple minutes again, yeah, but this is the crucial point. This is really driven by entropy. Factor of 2.
Well, the free energy. Different by that.
Yes. Yeah, but that factor of 2, I would say, is coming from the minus TS.
Yeah.
Yeah.
Well,
Well, I mean, the energy is, as I said, in our estimate here, it's kind of comparable. But I'll give you, yeah. Okay. Any other questions on these arguments? Yes.
Are the influence in this ordered state rough?
I mean, we haven't quantitatively analyzed this, but I think the domain walls probably are fairly similar to, okay, I think there was some numerics where we kind of briefly looked at like nucleating a solid out of a gas, and I couldn't see something that looked that different from usual like Ising coarsening. So,
one-half fluctuation.
well, I mean, we didn't quantitatively investigate so I don't want to put an exponent on it, but I don't see what I would expect it looks like Ising. Let me put it that way. Yeah, I think this is very much like the Ising model, except that this is flipped. That's the, we have order at high temperature. Now, okay. Yes. Okay. Let me now make a few kind of general comments about what's going on here. So, sometimes in physics it kind of helps to like rebrand something, and so we're going to rebrand this idea. In particular, maybe emphasizing the fact that this order persists all the way to very high temperature. We're going to name this kind of phase as an entropically ordered phase. I think it's very reasonable to argue that all of the sort of other examples of reentrance that we talked about yesterday, like the Pomeranchuk effect, Rochelle salt, and so on, I think it's fair to say that these are also manifestations of entropic order just at intermediate temperatures. But let me explain why we give it this name. So I've already said in words that the solid is really driven by having higher entropy, not by having lower energy. And we can give a sort of undergrad argument that has to be what's happening. So again, if we go back to our idea that we're minimizing the free energy. Suppose that we have a phase transition between two phases. We call them A and B. So phase B is realized at higher temperatures. Phase A is realized at lower temperatures. And here are the sort of free energy calculations from each phase. Not trying to be sort of too pedantic about this, but we could think of like FA as the contribution to the partition function from the sums over configurations that kind of look like this. And then in blue, it's the sum from terms that look like this. In any case, right, okay, so we have here phase A and here phase B. This is completely kind of model agnostic at the moment. So we always want to minimize F, right? So the curve sort of has to look like this. We have to kind of go from phase A at low temperatures. Its free energy curve has to sort of cross phase B and be sort of larger at temperatures sort of above this transition TC. So in particular, kind of just past TC, the slope in phase A has to be higher, less negative, okay? And okay, what does that imply? Well, by the laws of thermodynamics, we know that df dt is minus s. Okay. And so therefore, if this has a less negative slope, it means that this has smaller s and blue has higher s. Okay. So this is a very simple argument that we know for sure if we found a sort of phase transition, the higher temperature phase has higher entropy. And therefore, if the ordered phase is at higher temperatures, the ordered phase is the one with higher entropy. This is necessary. Yes. Yeah, so, okay. Yeah, in the example we've just been discussing, phase A is the gas, phase B is the solid. But, this argument doesn't rely on this specific model. It's completely general. These are just like, I've drawn it that way just to, okay, yes, if it's a continuous transition, we would need to sort of be a little bit more careful with the way these slopes line up at the transition, but the point is still the same. You go a little bit past the transition and you would find that the higher entropy phase is the one that wins at high temperature. Yeah, it's just a Taylor expansion. Yeah.
The way you conditioning is only valid for first order condition. Like if you have a second order condition, you just you have some non-incident slope, but you wouldn't imagine the phase that is beyond it.
So one way I could do this, right, as I said, I could take, let's say for the 2D Ising model, we could take the partition function and evaluate the contribution coming from terms that have magnetization between minus 10 to the 3 and plus 10 to the 3. We could call that the disordered phase, and all other states, we call them the ordered phase. We could ask sort of which contribution to the partition function wins. In this case, we'd have to go, of course, slightly past TC to see that the higher magnetization states dominate, but we would see that there's a sort of abrupt point where the higher magnetization contribution dominates. And if we went sort of a little bit past that transition, we would see that the sort of slope evaluated in this way is more negative in the ordered phase. Or sorry, in the disordered phase, because for the usual Ising model, we would have disorder at high temperature. But this is really just, these are kind of textbook thermodynamic arguments. So I'm not saying anything new here, but I'm just trying to really emphasize the point that without sort of detailed microscopic calculations, we know that the ordered phase here is sort of driven by entropy. Okay. Thus the name entropic order. Okay. All right. Okay, so then this begs the question, of course, so why can the ordered phase have higher entropy? And, again, I think I'm not really going to say something new here, but let me illustrate a sort of old idea in what I think is a very transparent model. Yes. Did you have a, oh, okay. All right, so let's sort of give some crude estimates for the entropy in each kind of phase. So I have over here, I'll have the solid phase. And okay, we've seen that in this solid phase, again, being slightly idealistic, only every other site on the square lattice is occupied. So the entropy is basically just sort of the number of particles on each occupied site. So it's L squared over 2, the number of occupied sites, times the sort of number of configurations that are accessible, which is log T. Okay. Okay. Now, what about the gas phase? So, here I'm going to be a little bit actually, okay, let me do it this way. So I'm going to come back to this minus sign in a moment. If we do the same sort of hand wavy argument for the gas, we get L squared log T over U to the 1/4. And naively, this is smaller. But of course, it would also have been smaller if we did this argument for any other system. So we need to be a little bit careful. And the thing we're sort of a little bit sloppy about here is that we could also say, well, in the solid phase, what if I had like little bubbles of different A and B sublattices kind of intermixed, like some kind of emulsion phase? Why does that not sort of have the highest entropy? And okay, without going through the Peierls argument, let me just say, like roughly relative to maybe what we would kind of naively expect in the gas, there's sort of a loss of entropy, and maybe at worst, it's sort of order 1 per site that comes from like picking which sublattice we wanted to be on. This is a very hand-wavy argument, but the point I want to make is that because the number of fluctuations are unbounded in this model, as we get to higher and higher temperature, we're always willing to sort of pay the entropic price for ordering by gaining the sort of bigger number of fluctuations in the ordered phase. So the sort of crucial point is that so ordering 1 degree of freedom, in this case, the sort of crystal, the solid, kind of overcompensates with larger n fluctuations. Okay, and this is why we have higher entropy. And if we go back to sort of other models that also have this reentrant order, you would make the exact same arguments. For example, with the Pomeranchuk effect, the story goes that when you heat the system up, when you heat helium up and you form a solid, there are isospin degrees of freedom that basically, unlike in the Fermi liquid, can now freely fluctuate. So ordering the translational degree of freedom in this case of liquid helium kind of enables isospin fluctuations, which overcompensate. It's the exact same effect. Okay, I think in this model, maybe it's just a little bit easier to see, at least in my personal view. But it's the same physics. Yeah.
The factor in like L squared over 4 versus L squared over 2. Right?
Yes, that's the point. That's why we picked the squared in the original Hamiltonian. If you picked a linear term, then you have 2 L squareds over 2, and you need to do a little more work to figure out what happens.
Order 1 number sitting in front that might.
But there's a log t. Oh, sorry, I'm also missing t here. There's, yeah. Or sorry, no, I'm not missing t here, but there's a t in the free energy. And anyway, this is, yeah. You're going to get at most something order 1 from sort of configurational degree of freedom, and it never beats log t. So, okay. All right. Let me make sort of a few more comments about this model. Okay. So the first comment is, so you might ask, well, what if the nx is sort of not allowed to get arbitrarily large, but it can only reach up to some maximal value k. Okay. So then, okay, one possibility is, of course, if that's all that we do, then we just go back to our old theorem from yesterday that we will always have disorder at high temperature. But there will be some sort of new critical temperature where the entropic order disappears, but this temperature will scale like k to some power. It depends on the specific choices in the Hamiltonian, if you used nn versus n squared, et cetera. Okay. But we know that we have this theorem, so like before calculating this Tc prime, we just know it's finite. So that's the end of the story in some sense. So, okay, you might be a little bit sad about that, but remember that, we don't need a superconductor at infinite Kelvin. We just want one at 300 Kelvin. Okay. So I think it's nice to have an organizing principle for boosting TC, even if, you know, the mathematical trick may not work in practice. The other thing I want to emphasize or stress is that you might ask, okay, well, what if we also, in addition to restricting these n's to be finite, what if we also just set this u to be infinity? So this would be what's called a hardcore lattice gas model. It means that we really restrict the configuration space, the state space, if you, I'm bad with jargon, so that no two adjacent sites can be occupied. Okay. And in this case, you know, this model has been studied to death in the 1970s and 80s. And the hardcore lattice gas is a solid if the fugacity z, which in our model would be just the sum from n equals 1 to k of e to the minus beta n, if this sum is larger than 3.7 something something. Okay. So this means that we just take k greater than or equal to 4, and if we have the hardcore lattice gas, we can still have order at arbitrarily high temperature. In this case, you could even say infinite temperature. The ensemble exists. So in this case, we still have order at arbitrarily high temperature, or as beta goes to 0. The theorem that we're invoking here, remember, relied on some assumptions, including that the configuration space was this kind of product space, and that, you know, each kind of local piece was finite dimensional. And if we break either one of those assumptions, we can see that it's very easy to get order at arbitrarily high temperature. All right. So let me just sort of spell that out explicitly. So the theorem on no order at high temperature, it needed, firstly, that we had, let me just sort of say finite configuration space, and we also needed this unconstrained omega. And in this same family of models, we see that both assumptions are necessary. Okay. So you can relax either one and get order at arbitrarily high temperature. All right. The last point I want to make about this model, I said it yesterday, so let me be very brief. Okay. We can ask the question, is entropic order a robust phenomenon? And I think that in the sort of most honest sense, the answer is no, because we can take our Hamiltonian and just modify it, you know, in some very simple way. Really, there are infinitely many ways to modify this Hamiltonian that that destroy the high temperature order. So as long as delta is positive, we have no entropic order, high temperature. But it's sort of the same thing that we already discussed. This is kind of analogous in some respects to capping the number of fluctuations at some large value k. In this example, we would still have sort of order for, let's say, temperatures between our original TC and some new TC double prime, which, you know, scales as epsilon to some negative power. So it still can be made arbitrarily large if epsilon is sufficiently small. Okay. So maybe we can qualify this with, as temperature goes to infinity, the entropic order is not robust, but, you know, perturbations kind of just give you a sort of transition back to disorder at very high temperature. Yes.
Entropy of the first phase again.
Yeah, so the gas again would win because you could think of like this power would now be slightly smaller than 1/2 and it would win. Or actually rather this one would change, but you get the point. Yeah.
Entropy again at the high temperature. Is that the same?
Yeah, it's similar, I would say, to the other examples in the literature. I mean, in the literature, all of the examples that I know sort of had this kind of like the reentrant order only exists in some intermediate window. So we just go back to that case, you know. Yeah.
Have any prediction of like quantum conversion in this model?
Yes. Yeah, I'll discuss. Oh, you mean of this?
Like the lattice.
So, okay, you could add quantum like hopping terms to this model. So that doesn't give you a quantum critical point. I think in some paper we'll hopefully put out in the not too distant future, we'll talk about like adding hopping terms to models like this and argue that, you know, it doesn't really do much. So we still get the entropic order. As for a quantum critical point, I'll hopefully get to that at the end of the lecture. There exists a conformal field theory describing that critical point that has.
Lattice theory, you don't.
I don't think anyone has explicitly written down the lattice theory, but I would, yeah. My hope is that if you know the CFT, that you can kind of guess what the lattice model might look like, because it'll be some like ON cross Z2 model. So, okay, you know, in principle, you could have some like O50 rotor on the lattice. It might not be practical, but there's no like. Yeah.
Want to pull this down to your feature.
Yeah, so in the CFT case, I'll show you. Yeah. So yeah, that's a different kind of transition because this is sort of strictly a thermal transition. And indeed, right, it's in the same universality class as the Ising model. So it's not really a new fixed point here, but I'll tell you about a new fixed point in a little bit.
High temperature.
I mean, if you can just somehow, you know, pull this solid phase down to temperature, and then see what the conflict is. Maybe it's not about.
I mean, I think it's a well-formed question, but the answer is we don't know how to push the solid all the way to 0 temperature in this model. But we have other models where there is a symmetry breaking that sort of goes down to 0 temperature. Yeah, at least in the continuum. Yes. Mm-hmm.
As the coefficient goes slightly above 0, I get a jump in the order parameter. Is that right?
Yes.
For any of these.
Yeah. If you're at sufficiently high temperature, the jump would be very drastic. Yeah.
And state that I get here, will it have a big ferromagnetic correlation rate?
In the ordered phase, before you turn on the perturbation, yeah, I think I would expect that it's, okay, let me say, actually, yeah, if you turn on the perturbation, so you destroy the long-range order, but we asked what the correlation length is, I think it probably depends on T, honestly. Like if T is large enough, probably the correlation length is immediately super short. But it's I think the issue is somehow that when you're at very high temperature, right, a perturbation like this is not necessarily so small because the coefficient here, think of like, if n is of order T, then it's like epsilon times T to the 2 plus delta. For some large enough T, this is actually a huge perturbation. So that's, I think in some sense, the order may be kind of sick. Like it matters whether you first take epsilon to 0 or T to infinity.
As you tune epsilon 0.
I'm not sure I would agree with that. I think it's probably a second order transition, but the epsilon C vanishes with temperature at high temperature. It's like T to the minus.
High temperature?
Yes. Oh, then for some small enough epsilon, the order persists. And then you get a continuous transition. If you fix temperature first. Right, because if you fix T first, then you need to increase epsilon to this. Like, you just have to invert the logic here. So at a fixed T, for small enough epsilon, you're below TC double prime.
For which I need for order.
No. No, you would need an infinite order polynomial to do it, if you're fixing T first.
Exactly, so there's a big enough power of n that I can add at a fixed T. If you destroy order at that T.
No, because it's just the polynomial power changes this. It doesn't take TC double prime to a sort of finite value. So all the TC double primes will still diverge with some power of epsilon, but it's just this exponent will get smaller. Yeah.
So the integral relation, we should.
It still doesn't. I mean, we still violate this one, but we just go back to what looks like a more typical phase diagram. Okay, let me keep going. There are a few other things I want to discuss. Okay, for the rest of the lecture, I kind of wanted to show you like how to engineer entropic order. So you might think, okay, you just like had a dream and came up with this cute model, but like that's it. There's nothing else in nature or in math that can do this. But this is not true. So let me show you two kind of tricks or perspectives for building entropic ordered phases in other settings. So the first trick I'll discuss is sort of using what you might call like link bosons to transmute high and low temperature. Transmute here just means flip. So you'll see what this means very shortly. Okay, so let's go back to the sort of classical 2D Ising model, just it's the simplest illustration of this. We have, right, in the usual Ising model, we have just the Ising spins on each lattice site. They can be +1 or -1. And now to this model, we're just going to add a boson on every link. So this is the link boson NXY, obviously for X and Y nearest neighbors. And this is just a non-negative integer as before. Okay. And the Hamiltonian that we're going to consider is the following. Okay. It's a bit contrived, but it's a mathematically sensible Hamiltonian. You can check just like we did before that the partition function exists at any finite beta, so the model isn't sort of overly sick. Oh, right. That's of course assuming that we choose A, let's just say A larger than B larger than 0. Okay. If we need to sort of choose the parameters in this regime so that there's no like unbounded negative energy states. Okay. Now, if we do this, we can evaluate the partition function pretty easily. Well, at least partly pretty easily. So we can, of course, sum over Sx or Nxy in either order. Why don't we sum over Nxy first? So if we do the sum over Nxy first, right, we get something like this. E to the minus beta Nxy times A minus B Sx Sy. And of course, this sum is just our favorite geometric series. And the point is that Sx Sy, right, can only take two values, +1 or -1. So we can, of course, rewrite this formula as right, 1 over 1 minus e to the minus beta A minus B. If S1, S2 equals 1. And I'm being pedantic here because, as you'll see shortly, we can nicely rewrite this formula as e to the A plus B, S1, S2, where these parameters A and B are defined as follows. Well, okay. Let me save 20 seconds by only writing down B. So this probably should be, yeah, okay. Okay, so there we go. So now you see the point. So Z of beta in this model is just the sum over spins of e to the b, which depends on beta, times the sum over x adjacent to y of sx times sy. This is the 2D Ising model. Okay. So it's equal to like 2D Ising partition function at effective inverse temperature B. Okay. And now, if we just sort of look at this function B, so, okay, let me go over here. So, this function B is actually decreasing as beta increases. So it basically sort of flips increasing temperature to decreasing temperature. So we get a plot that looks something like this. This value is just a plus b over a minus b, so it's finite. You could have picked a sort of weirder function if you wanted b of 0 to diverge, but this is the simplest model and it's just finite. Okay. Now the 2D Ising model has let's say a critical value of b at log of 1 plus square root 2 over 2. Okay. And so after a few lines of algebra, you can show that we want 1 to be smaller than a over b to be smaller than 1 plus square root 2. If we make this choice, then the phase diagram will look like this. So at low temperature, we have the ferromagnet phase, or sorry, paramagnet phase, which is ordered. And then at sufficiently high temperature, we have the ferromagnet or the Z2 broken or ordered phase. Okay. And the 2D Ising model has been solved mathematically, so this is here's a model, we can solve it exactly, and it has order at arbitrarily high temperature. Okay. So this is just a cute gimmick, but you can do this to any model, or at least many families of models that you want. Classically, it's fairly simple. So, yeah. I think the bosons have absolutely no or very limited correlations with each other. Yeah.
So the physics is that you start populating bosons with high temperature, and that cranks up the change coupling for the Ising model.
Yeah, I'll explain. Yeah, I'll explain.
Okay.
Yeah, in a few minutes. Yeah. Okay. Let me. Yeah. Okay. Good point. Before I move on, let me just kind of illustrate the physics. It's actually, in this sense, a cleaner illustration than what I said before. We can sort of see why we're getting order at high temperature by the following argument. So we can again kind of estimate the entropy in the ordered phase. So in the ordered phase, we have roughly L squared times the log of the number of bosons in the ordered phase. And this is L squared log T over A minus B. kind of crudely speaking. This is the typical number of bosons that we've excited. And the A minus B, right, is because if most spins are aligned, then that's the sort of typical kind of cost to create a single boson. Okay, in the disordered phase, in contrast, we have L squared log of n bar in the disordered phase, but we also get this kind of configurational entropy. Like we're not restricted. Yeah, we have like spin fluctuations that have a much higher entropy. So being very sloppy about it, we could say we get extra spin fluctuation entropy. Here we have bosons. Here, this is the bosonic contribution. And we can again kind of estimate this contribution. It's L squared log of T over A plus B. So in this model, the T log T's drop out, but this is again a kind of crude estimate. But the crucial thing is that the T also comes with this kind of constant prefactor. And so if A minus B is sort of sufficiently small, you can see that this entropy will sort of beat this plus this. It's again a kind of colloquium level argument, but this is the way to see what's happening. So at high temperature, there's so many bosons, and you get so many more bosons if you happen to sort of order the spins that this is actually the preferred typical configuration in the Gibbs ensemble. Okay. Oh, because if Sx, Sy, I mean, you could maybe say like, I don't know, if we want to be pedantic, maybe it's something like this, like on average, half the time you see an A plus B, half the time you see an A minus B. But the point is that this prefactor will be different in the two phases. Yeah. Okay. All right.
Here, the fact that this kind of temperature difference doesn't mean that it could be more fragile with dark temperatures to dimensions.
I don't know what you mean by more. It kind of somehow infinity is it's a delicate word, but it's probably as fragile in.
Because they went to large temperatures, the entropy difference between the two phases scaled with temperature. Right? Here it doesn't. You have like a very large entropy of the four phases and a small jump in temperature.
Okay, sure. So maybe you could say like I could see it being possible that you could add a boson independent perturbation to this model that destroys order, even at high temperature. And that would not have been true. Like you wouldn't have been able to add something bounded in the bosonic model. So in that sense, I would agree with you. But, all right. Let me just sort of give you one other, just very brief kind of example along similar lines, just to point out that you can really sort of apply this trick to many models. Not all, but let me tell you a quantum one where it also works. So, okay, so let's take what you might call a quantum stabilizer code. So very schematically, the Hamiltonian will look something like sum over, this is kind of the usual case. It would be like a sum over, X products of poly X's. In the toric code, these might be like X's around every other plaquette in the lattice, if qubits are on vertices, and you could have Z's on the sort of alternating plaquettes. Anyway, let me just kind of abstract this away to just minus the sum over stabilizers S, SA, and these stabilizers are all commuting. This is very important for this trick, okay? There exist stabilizer codes that at sufficiently low temperature have topological order in their thermal ensemble. So if you like, this means that these codes are kind of quantum memories that protect logical information at finite temperature. It's not necessary, but it's sufficient. Okay. The simplest and kind of the first known example of this was the 4D toric code, which has finite T topological order, and I'm not going to write down sort of the form of these X and Z, but they're in the literature, of course. Okay. So to the 4D code with this quantum Hamiltonian, we can now like make our entropically ordered topological order at high temperature by just doing the exact same trick. So to each stabilizer S, we add a fluctuating, let me call this alpha. So to each stabilizer, we add a boson N alpha, and it's the same thing, okay? Because all of the S commute, you can exactly evaluate the partition function of this model and show it reduces to the partition function of this model. The probability of finding, any specific quantum state reduced density matrix on the qubits is identical to what you would have at this model at some other effective temperature. And so again, you can just choose A and B such that at arbitrarily high temperature, this model has topological order. So if you remember, yesterday I had mentioned that there was sort of a lot of interest in quantum computer science about the kind of triviality of these high temperature Gibbs states. So this is a kind of clear illustration that relies on this assumption of finite dimensional Hilbert space. The moment you work with bosons, here's a simple example that not only has entanglement in the high temperature Gibbs state, but it's sort of the strongest kind of entanglement possible. Like almost every state, Gibbs state, has topological order. All right, any questions? I put it in by hand. These are the link bosons from before. The point is that this link boson allows you to kind of transmute high and low temperature as long as you have some commuting Hamiltonian or a classical model. But either way, you're allowed to sort of exactly sum over these n's to evaluate the partition function. That's the trick that we're using. Yes.
You have like a tip that is working with size
So I would say if you take like the 2D toric code where you have these stabilizers live on plaquettes, then you just, on every plaquette, you put an independent boson. But basically, it's one boson for each parity check. Yes.
And then how we take the limit in the K and determine about the order?
No. No. For any finite K, there will be some finite TC prime. Well, I would say like you just never have topological order in the 2D toric code, but you would get sort of closer and closer if you made this Hamiltonian a little bit different so that this B function diverged at low temperature, you would get like closer and closer to topological order, but you would never reach it. Yeah. Yeah.
Can I document Embry Mars, for example? About energy.
So, I guess I haven't thought about the Embry-Ma perspective here. We have some very brief comments in the paper that like you could use the same trick if you wanted to realize like spin glass order at high temperature. I mean, it's really exactly the same argument. But
that spin glass is different. I'm talking about
yeah,
the ferromagnets being stable to, let's say, around the temp.
yeah, and that question I haven't thought directly about, but it could be interesting. All right. So I think the last thing I wanted to discuss a bit is the kind of field theorist perspective on this problem. So I discussed this a bit yesterday. This was how I got interested in this problem. I was sort of visiting Zohar, and he told me that he could make high temperature order, and I was like, that's bullshit, because I know of all these theorems that everything is completely featureless at high temperature. And he points out that, field theories avoid all of these theorems, which is certainly true. But still, it was kind of a very physically surprising thing to me that high temperature order was possible. So let's sort of return to where we began historically, or I began historically, and discuss a little bit about quantum field theories. So, okay. So again, just to sort of recap from yesterday, our goal is to say we have, let's say, a quantum field theory with some kind of quantum critical point here. Maybe ideally, this can even be a conformal field theory. Just, if it's a conformal field theory, then the mathematicians are about as happy as they're ever going to be with QFTs. And so let's aim for this. And our goal is basically to have, a phase diagram that looks like this, where we have order and disorder here. So spontaneous symmetry breaking sort of at arbitrarily high temperature. And in particular, if I sort of follow the line, starting from the critical point and just going up in temperature, I might expect that if I have some order parameter, which I'll call psi for good measure, I might expect that the expectation value of psi scales as temperature to some power in the kind of crude physics sense, where we restrict to one replica. Okay. And why does it have to be this? Well, if we have a conformal field theory, we would have scale invariance. And so this is sort of the most general thing we could hope for. Okay. So this is our goal. Does this theory exist? Okay. And the spoiler is that it does. And, it's a little bit messy. So let me try to tell you a bit more about how one checks for this in field theory. And then I'll just write down a sort of moral Lagrangian for you that tells you what this theory looks like. Okay. So basically, to look for entropic order, we're thinking about QFTs at finite temperature. It's natural to evaluate, of course, the partition function. Field theorists don't usually work with a Hamiltonian like this. It's more natural, of course, to work with a path integral. So if we have some set of fields phi, then we're evaluating, let's say, the kind of Euclidean time action where this SE will be an integral over the imaginary time thermal circle and any spatial directions of, a Lagrangian that depends on phi, and d mu phi, and so on. Okay. Okay, so all we have to do then is sort of find the right Lagrangian and calculate. And what are we hoping to see in our calculation? So the sort of general philosophy, which goes back to the 1970s, is as follows. So, okay, so let's suppose that we don't have let's say that whatever kind of order we see, it doesn't spontaneously break any translation or space-time symmetries, et cetera. It's just maybe breaking some Z2 flavor symmetry. Okay. In this case, we might expect that there's a kind of vacuum, although I really hate that terminology here, but there's a kind of typical configuration of the field. Here, I'm just going to put one for simplicity, but we'll see that we need multiple to realize this in any example I know of. So imagine that there's some homogeneous typical value that you see in the ensemble, and then there's some kind of small fluctuations about this kind of homogeneous vacuum or typical state. It's really not the vacuum because, of course, we're at finite temperature, but I don't know, sometimes the jargon just sticks. So, okay, so we make this guess, and then there's a kind of philosophy that, as I mentioned, goes back to the old days where one essentially can think of z of beta as a path integral over, you know, the fluctuation or right. So you can think about like an ordinary integral over this homogeneous background value, right? You do a path integral over all of the fluctuations. The fluctuations, of course, are restricted to have like 0 Fourier modes at 0. It's just a rewriting of phi. And the idea is that what we'd like to do is to compute a kind of effective free energy so there's a kind of effective free energy density of this model that depends on the choice of phi bar. Okay. And of course, in the thermodynamic limit, this integral would be done by saddle point, and we see that so sort of phi bar is chosen so that this F effective is minimized. Okay. All right.
Replica, as you call it.
Well, so what would happen in the Z2 symmetry breaking cases, of course, this F would be an even function of phi or psi, and you would find just two exactly equal minima.
No, but what I mean is formally in this path integral, integrating over phi tilde, you're not really allowing it to go to the other replica. Otherwise, you get 0.
No, you are. Like this delta phi could have huge fluctuations. This is just a formal rewriting. That we'll see that we make approximations that's basically neglected. But so far, it's just rewriting. Yes.
Why did the beta front?
Oh, I mean, well, I've just defined this function to be whatever this path integral is. So it's a semantic thing. Yeah. Oh, yeah. Yes. Yeah. Of course. Okay. All right. So, right. So far, this is all semantic. And we actually have to sort of evaluate that F effective, which is, of course, always the hard thing in field theory is to actually do anything. So, all right. So we need to evaluate this F effective. And remember, everything is hard in field theory. So what's commonly done is just to, so we're trying to evaluate this thing. This was this integral over the fluctuations of e to the minus s of phi bar plus delta phi. And so usually this is now to Leo's point. A priori, this path integral includes like instanton-like configurations that sort of kick you from one local minimum to another, but we're lazy. And so what we're going to do is sort of approximate that the delta phi path integral can be done as a Gaussian path integral. And, you know, often in field theory, one invokes tricks like large N or an epsilon expansion to make that sort of a more justifiable step. But for the moment, let me just be sort of generic and say this is kind of an approximation that Right, okay. So, there's some kind of integral x prime, delta phi of x. There's some operator here, delta phi of x prime. And then, of course, this path integral can be done explicitly, and you get some kind of trace log as usual. Depends on whether, of course, you have fermions or bosons, whether there's a sign and so on. But that's sort of the essential strategy. Okay. So now there's an old story that goes back to, at least I think it's usually attributed. I never know with history whether I'm just like bullshitting and like the real hero is not getting any credit. But I think it's just Weinberg, in this case, in 1974, sort of asked this question of, was it possible that this effective free energy maybe sort of had a symmetric minimum at 0 temperature, but a symmetry broken one at finite temperature? Okay. So you could ask, like, is the minimum of F effective of phi, let's say, at a sort of symmetric point, maybe phi bar equals 0, at 0 temperature, and a broken configuration, maybe phi bar not equals 0 at finite temperature. And I think he was inspired by this old Rochelle salt story that I mentioned. There's some kind of cosmological implication that people have thought about. I don't remember. Maybe Weinberg didn't care about that in 1974. But anyway, there's a sort of old history of this in field theory. Yeah.
The second line was done.
Oh, sorry. Yes. Let me erase that. Thank you. Okay. All right. So at this point, maybe, yes.
Not just a scalar function, right? It includes derivative.
Oh, yes. Yeah. I mean, sloppy, but yes. It's a functional, of course. Well, wait. Actually, no. Sorry. It is because we said phi bar is a constant, right? So, yeah. If we had put a phi bar of x, then yes, you're right. We would worry about something more complicated.
That kept having to minimize.
I mean, I think if you did this path integral legitimately, it would, because, right, this, well, okay, I guess what you'd have to check is that the fluctuations in delta phi aren't dominated by like instantons. But yeah, I mean,
Very delicate.
in the,
You could say, you just change variables. So that delta phi path integral, if you did it exactly, would not depend on phi bar. You just change variables.
no, because of this constraint. So there's something left. I mean, I agree. So I agree that it's
Background, you want to introduce sources and then, Lagrange transform, then it's more legitimate. But
what's the difference? I mean, that's if I introduce a background field, it's the
there's something left over. This is just to change your variables.
okay.
Anyway,
I don't believe that, but that's fine. I mean, I agree it's delicate. I agree it's delicate, but there's
because ultimately that delta phi integral is doing the background field method. You do it approximately around a particular minimum. You don't do it include.
But that's exactly the same thing that is, I mean, it's the same approximations that are done here. And I think this is just because, as I said, like field theories are hard. And so the only thing we know how to do basically is a Gaussian integral. So, leading order, someone would be offended, but. Okay, I don't think I agree with that, but anyway. In any case, so this is what one does. And Right. So at this point, I mean, if you're a particle physicist in 1974, the only thing you know are like relativistic quantum field theories, and there's sort of a finite list of things you check, right? So there's like the phi to the 4, there's the scalar theory, you could have a fermion, you could have a gauge field. You check all permutations of those models and see what happens. The simplest one, which I'll just very briefly sketch, would be, so maybe try 1 is like a scalar field theory. So, okay, the Lagrangian is like 1/2 d mu phi squared plus, being a bit sloppy here, but plus, lambda phi to the 4th. And okay, if you do this path integral, what do you find? Well, okay, after some calculation, you get that this effective potential looks basically like lambda over 4 factorial phi bar to the 4 plus there's some constant t. I think you get t to the d minus 1. This is in d spatial dimensions. And yeah, there are sort of higher order things that are difficult to compute, or at least to Taylor expand. But okay, morally, one can do this this like one loop approximation to the path integral. Oh, and the important thing is that this number c is positive. Okay, now that's bad because it means that, right, what's happened? Well, bad depending on your perspective. What it means is that at finite temperature, the fluctuations tend to kind of restore the symmetry. If we were trying to sort of break a Z2 symmetry phi to minus phi, the fluctuations are trying to restore the symmetry. And this is, of course, in line with our physical intuition, right? That fluctuations tend to sort of restore symmetries, not break them. So maybe you should be happy that field theory doesn't disagree with all of the lattice models we've been talking about, like the Ising model. Okay, now, if you think about this example for a while, you may notice that if I add more scalar fields, I mean, I'm basically going to do the exact same path integral. All that's going to change are like, depending on, maybe some quartic scalar 1, scalar 2 couplings, like it'll be this coefficient C multiplied by whatever the various, let's say, quartic couplings in the theory are. And you could find a theory, perhaps, where some of these quartic couplings are negative. Okay. Let me give you a sort of cartoon example of this. So more successful try number 2 will be what's, I think, called the biconical model. So this is going to be a sort of ON cross Z2 symmetric field theory. And okay, let me write down the kind of the most egregious formulation of this problem. So here, this label A goes from 1 to n. We have the scalar. So this is just a Z2 scalar psi. And then the sort of quartic coupling will look like this. So and depending on dimension, there can be more terms that you need to write down here. Okay. So if you look at this model, so we have a minus sign here. I mean, the model is still sort of positive, like the original phi to the 4th theory. So it doesn't seem like it ought to be sick. But we do have a minus sign here. So we might hope that when we do the same thermal mass computation, we find something more exciting. And indeed, Weinberg did this calculation and found the following. So this effective free energy is something like lambda n for 4, 5 r to the 4. There's all the kind of, vacuum-like terms. And the thermal mass term, I don't know, there's some C, maybe it's normalization factors have changed, so who knows? Anyway, you get something like this. I'm being lazy, but the point is that you indeed get a minus sign on the thermal mass for the second term. Right? So that was known a long time ago. So you might ask, okay, so the story ends here. Okay. So there's sort of two maybe small technical challenges that one has to worry about here. The first is that this model is not UV complete. So this is a kind of low energy EFT. And from this perspective, it's a low energy EFT that definitely has a kind of reentrant order. That's clear. But it's not necessarily a model of high temperature order because this theory doesn't exist at high temperature. Doesn't make sense. Okay. Another, let's see. Yeah.
Low temperature, the decoupled fixed point.
So I think Weinberg did this calculation in 3+1 dimensions. So it's, I mean.
Presumably the decoupled fixed point is stable. But then there's no universal reason to expect one or the other sign of your coupling.
So, okay, let me come to that point. Since I only have a few minutes left. Okay, I forgot the second thing I wanted to, oh, right. The second thing I wanted to say here is that at least the way I've written down the model here, in this cartoon model, you need to be a little bit careful because actually it's not obvious what the correct vacuum of the theory is. In this model, if you're a little bit more careful, you sort of notice that it turns out you need, let's say, 1/n corrections to find the sort of true vacuum at t = 0. This is just sort of a technical issue. You can see it because if you just try to minimize this term, like phi bar squared minus psi bar squared equals 0, seems like it, there's a flat direction naively. And so you might worry that it doesn't look like the CFT that we wanted there if you have this flat direction. Okay, so let me just sort of comment that, so these are the things that Zohar and Fedor solved last year and sort of kicked off our kind of subsequent work. So, okay, basically the short story is that you take this biconical model and, okay, writing it in maybe a sort of more modern way, we have our ON field, we have psi. Let me do a kind of Hubbard-Stratanovich transformation on that coupling. So I have, and indeed, there's a sort of question about the sign here. So let me put T for the moment, that's some coupling constant. There's a relevant, or sorry, a marginal tree level coupling like this. So now we're in D equals 2. So in D equals 2, this theory should exist and should be UV complete. Okay, and there are various relevant parameters that you have to turn off. So there's phi squared, psi squared, psi to the 4, sigma, and so on. So it's a multi-critical point, but there's a finite number of relevant operators. Okay. So the things you have to check in this theory are that, so firstly, you check that, so what are the sort of fixed points at large but finite n? So they're basically fixed points with t equals plus or minus 1. So you evaluate the beta function and find it vanishes at either of these values. So we just take the one at plus 1. Why not? This theory seems to exist in the space of CFTs. The second thing one can do with this theory is check that the true vacuum is at t equals 0 is phi bar and psi bar are 0. Well, actually, let me just write this. I don't strictly remember phi bar, but so the vacuum at t equals 0 is symmetric. And then 3, you can sort of, the large N kind of controls this computation of the effective free energy. And you find that psi bar squared scales like some number times square root t. Okay. So this is a conformal field theory. As far as we can tell, it exists. It's a unitary CFT, and it spontaneously breaks symmetry at any finite temperature. And so, yeah, I've kind of walked you backwards through the way that we thought about this subject, but yes. Yeah.
There are no temperature dependencies in the coefficient of the CFT.
Yes.
Of this.
Yeah. The CFT, there's some G star,
But there's
t equals 1.
There's no implicit temperature dependence in G and C.
No.
That's the.
Do you have any intuition from why this field theory is getting this order, and is there any relation to your lattice model?
Right. So I would argue that, so this is a model. So in this sort of entropic order paper, we discussed this model, and we sort of do the calculation from more of our recent perspective, and you can indeed show that it's entropic order quite explicitly. But what's happening is basically, you can sort of see over here, right? So the idea is that the thermal mass there's many fluctuations of these phi a's because you have a large n number of fields, right? And you can maybe crudely think that, like, if you're at finite temperature, the phi have a thermal mass, and so their contribution to the partition function is kind of reduced by this. But if I happen to have this psi squared, then it kind of lowers the energy of having the sort of typical thermal fluctuations that I know I'm going to have anyway. So the picture is like, if you just order psi, then you lower the thermal mass of the phis, and there's a large n number of phis, and so lowering that thermal mass is sort of more important than losing a small amount of entropy from ordering psi. So it's kind of exactly the same story where in the crystal, you would just like break the Z2 symmetry to gain number fluctuations. Here, you're breaking the Z2 symmetry on psi to gain number fluctuations in phi. No, so here, right. So let me make one last remark on that. So people have done numerics on these models. I don't know how, but people have done this. And it seems like maybe n roughly around 10 is needed to see finite temperature order. So if it's a CFT, yes. You only have to check one temperature that's not 0. Yeah. So the claim is that the CFT exists, and I think there's no reason the CFT doesn't exist at finite n. It's just we don't have control over the exact critical exponent.
I don't know, it makes sense to try to think of a lattice regularization of the theory and see how it correlates to your theorems.
Yeah, and I think people may have even now that I think about it, people did numerics at least in some models, so there is some regularization of this that people have already looked at. Yeah, but you could have other bosonic degrees of freedom. So, like, one perspective on what we've done that I could maybe sort of also end with is that, maybe from the field theorist perspective, the nice thing about this like lattice model that I showed you is that it gives you a regularization of a theory with high temperature order where the order at high temperature is not cut off by by finite size effects or, lattice bandwidth, et cetera. So it's sort of like there exist ways of simulating a model with high temperature order where the sort of regularization is faithful to the phase diagram. And so I don't think they did that in their numerics. So it might have been more subtle what they were doing, but yeah, they probably just took some rotor model with a Z2 degree of freedom and said, well, temperature is small compared to lambda or something. Not sure. There are references in our paper to this paper. Okay. But I guess, well, are you saying it's sort of re-entrant and?
More like visual order sliding and higher. I don't know whether it's
I see. Yeah, I mean, I can basically stop here. Yeah.